Hello everyone, I am Zhihua, a fifth-year PhD candidate from the Hong Kong University of Science and Technology. Today, I will present the paper ShortcutLens, a visual analytics approach for exploring shortcuts in natural language understanding datasets. This is joint work with Cornell University, ETH Zurich, Peking University, and Huamin Arts Lab. Benchmark datasets play a fundamental role in natural language understanding by providing grounds for model evaluation and comparison. GRU is one such example, which has been widely accepted in assessing models' NLU capability, which can benefit downstream applications. However, shortcuts, unwanted bias, in the datasets can mislead the development of natural language models. Shortcut solution performs well on the training sets and IID test sets, but cannot perform well in the OOD test sets. There are massive shortcuts found in the literature, but there is a lack of a hierarchical and interpretable way to help dataset creators mitigate the shortcuts that exist in the natural language understanding datasets. Building a high-quality benchmark dataset is beyond simply collecting random examples. High-quality benchmark datasets typically has two common properties: challenging and pertinent. Challenging means that the benchmark dataset is capable of revealing the gaps between different models. For example, we don't want simple models easily achieving human-level performance in the benchmark datasets. Pertinent means that the model's performance on the benchmark datasets should reflect its capability in the target task. For example, for spatial reasoning tasks, we don't want the model to use shortcuts to make accurate predictions. To mitigate the effects of shortcuts and build a high-quality benchmark dataset, we would like to see a way to address how to help dataset creators develop a systematic understanding of shortcuts in the NLU datasets via visual analytics approach. Previous work includes adversarial text generation and temporal, which can help summarize the query datasets. However, they cannot help summarize the shortcuts in the datasets. Temporal cannot work for non-text and does not conduct a void analysis of potential templates. DQI can investigate some shallow shortcuts, but fail to provide an interpretable, hierarchical, and unified way to present shortcuts. We propose ShortcutLens, a visual analytics system designed to assist dataset creators in investigating shortcuts within NLU datasets. It presents an interpretable and hierarchical approach, offering a unified method for representing various kinds of shortcuts. Inspired by previous work on shortcut definition and summarization templates, in this work, we consider a specific kind of matching-based shortcuts based on a set of spatially related words. Parts of speech of the words will need to be first determined. Then we will follow a decision rule to judge whether the sentence is matched by these shortcuts. In this example, consider these shortcuts. The first word is determinant, another word is behind two words of it, and the second word is word view. Then you can match this sentence follow this order of judgment. For this sentence, it does not have determinant, then it cannot be covered by these shortcuts. Since the scope of potential shortcuts could be very large, we would like to select the shortcuts which have great effects on dataset quality. Specifically, we would like to select shortcuts with high productivity and coverage. Consider the dataset with 3 sentences, and the shortcuts concerning the first word is none. The coverage of these shortcuts is defined as the number of instances covered by these shortcuts. We can see these shortcuts matching all of them, then the coverage is 3. The prediction label of the potential shortcuts is defined as the dominant label in the label distribution. For these shortcuts, it matches 2 true instances and 1 false instances. The dominant label is true, then the prediction label is true. The productivity is calculated as the percentage of covered instances with the same label as the precision label in covered instances. 2 of 3 have the same label with the petition label, then the productivity is 0.67. It is expected to have series of algorithms to mine the shortcuts from the datasets. We designed a shortcut mining algorithm to extract shortcuts with high productivity and coverage from the datasets. We first enumerate potential shortcuts from the datasets, which fall into the scope of the defined shortcuts. Then we calculate statistics of them and filter them with high productivity and coverage. We finally organize them into a hierarchical structure like this. The parents of the shortcuts can cover the instances covered by the children by definition. After running the shortcut mining algorithm, we find that there are a large number of potential shortcuts in the benchmark datasets. One of the reasons is that the number of different words is quite large. It imposes difficulty for users to explore such large-scale potential shortcuts. Therefore, we further design an algorithm to aggregate similar potential shortcuts based on the semantic meaning of the shortcuts to reduce the difficulty for users to explore. The basic idea of the shortcut aggregation algorithm is using hierarchical clustering to aggregate potential shortcuts with similar words based on word embedding into a new shortcut and insert these shortcuts into the original hierarchy of shortcuts. It can mitigate the burden for users to explore the hierarchical shortcuts. To estimate the influence of the removal of a group of instances covered by shortcuts, we will calculate machine accuracy on different sets and productivity of the shortcuts. We consider dirty sets as instances covered by shortcuts and clean sets as instances not covered by shortcuts. Whole sets consist of all instances in the specific test sets. When calculating productivity for a group of shortcuts, there may exist instances with different prediction labels of shortcuts. It is counted into number of degree and will not be used in calculating productivity. It is interesting to compare the machine accuracy between the whole sets and the clean sets to see whether the removal of potential shortcuts leads to the degrading of the performance metrics in the clean sets. Such indicators can help dataset creators understand the potential benefits gained from the removal of the instances covered by those potential shortcuts. ShortcutLens enables users to conduct multi-level exploration of shortcuts and gain insights on how to fix them. The interface of ShortcutLens consists of control panel, statistic view, template view, and instance view. Control panel allows users to select different datasets. The statistic views helps users grasp the statistics such as coverage and productivity of potential shortcuts in the datasets. The template view employs hierarchical and interpretable templates to summarize different types of shortcuts. The instance view allows users to check the corresponding instances covered by the shortcuts. We introduced the case study one with the expert E1. E1 chose to inspect the shortcuts in space 2021. E1 found that the percentage of instances with the label false in the test set is 0.54, while the average measuring accuracy on the test set is 0.69. Given the situation that the model performance is quite good, E1 decided to further explore the potential shortcuts in the datasets. E1 set the minimum productivity as 0.75 and the minimum coverage as 100 to filter the potential shortcuts. E1 found that most potential shortcuts consist of locality words. E1 selected the shortcuts with the locality word left with long words ahead in the projection plane and checked the what-if analyze plane. E1 found that these potential shortcuts covers 15 instances in the test sets with productivity of 1. In the dirty sets, which includes instances covered by these shortcuts, the machine accuracy achieves 0.963. E1 thought that these instances are easier to answer as the models can exploit this type of shortcuts. Then E1 inspected the children of the potential shortcuts. E1 noticed some trial shortcuts with low productivity, like temporal left, which indicates that there are some cases battling against these potential shortcuts. However, this potential shortcut covers 143 instances in total and with high productivity of 0.87, which means that other children of these shortcuts tend to have high productivity. E1 further checked the instance view and found that it really coincides with the Wang pieces of the original test. However, such bias distribution worried E1 because it did not want such a shortcut to influence the model performance, especially when checking the model performance on the dataset. E1 said that he would try to avoid this kind of shortcuts in the new dataset construction process. For example, by reducing the number of locality words with left. In conclusion, we present a visual analytics system to help dataset creators to understand and mitigate potential shortcuts in the process of constructing benchmark. Case studies and expert interviews are conducted to evaluate the effectiveness and usability of the visual analytics system. Extension of ShortcutLens includes investigating more complex shortcuts in aerial benchmark datasets, supporting shortcut exploration for more diverse aerial tasks and benchmark datasets, enabling interactive shortcut fixing, improving scalability of visual designs to handle a larger number of instances and classes, and conducting a long-term evaluation of the effectiveness of the system. Thank you for your listening.